So in Mises' special seminar series, I have the pleasure today to introduce Professor Bjorn, who is director at the Max Planck Institute for Meteorology in Hamburg.
Thanks a lot, Frida. It's great to be here. It's a department that many of us know in the field. It's, in a way, sort of Bohlin's old stomping grounds, and Bjorn was the person who was responsible for the Max Planck Society having an institute in meteorology. So when the Max Planck president was trying to think if he should cut into the field of climate research, he went to Bjorn and asked, should we do climate research and who should we have? And that led to Hasselmann being appointed. So in some way we have roots here. So it's a pleasure to be here. Also, some of the people on the wall back there, particularly Henning Rode, have been quite influential. So it's another nice reason to be here. But another really important reason to be here, other than meeting Frida, is to check on Eula here, because she's doing her master's, and we had to come here to make sure she's behaving okay. So if she's not doing okay, then you have to let me know. So I'm going to talk about next generation climate models. And I wanted to start with this slide, the Paris Agreement, because I think it has an element of a phase change in the field, and I will try to convince you that that's the case. And so when I was reading through the Paris Agreement for this talk, I was struck by the fact that it never says carbon dioxide in the whole agreement. It says carbon in a few places. It mostly talks about greenhouse gas emissions. And it doesn't really say that greenhouse gas emissions lead to a warming climate in the agreement. So I always thought, well, the world accepted that fact. And they do it only implicitly. And so if you look at Article 2, they say, the Paris Agreement aims to strengthen the global response to the threat of climate change. Okay, so climate change is a threat. Where is it coming from? How do we measure it? They say we can kind of pace climate change by the temperature increase. Because keeping the temperature down would reduce the risks of climate change and impacts. So climate change can be reduced by not letting temperature rise too much. And to do this, one of the things we want to do is to reduce greenhouse gas emissions. So there you have it in the Paris Agreement. This implicitly recognizes the connection between greenhouse gas emissions and global temperature. So in that way, even though it's fairly indirect, you can say our science has made a fantastic contribution to society because we've essentially connected these dots. This is a nice picture I found of a coal-fired power plant. I like it because it's so clean and sunny and crystalline in the picture. So because normally we like to show dirty images, clean coal. Anyway, so we've connected the dots between fossil fuel burning, increasing CO2, and temperature. Done. Finished. We know that humans cause increases in CO2, and we understand why increasing atmospheric CO2 leads to temperature rises. And we can measure these things. So this is a terrific success. We can say that we understand how that works. And it's really, by reasonable people, not disputed. And I think as a science, we shouldn't spend time wasting our energy on unreasonable people. Because, yeah. We don't only know that. We don't only know that CO2 causes warming and that humans are responsible. We know some other things. We can roughly say how much. So we can say that we get about a half to 1.2, 0.4 to 1.2 Kelvin of warming per unit watt per square meter of radiative forcing. We have a pretty good idea of how much radiative forcing we get from a given amount of greenhouse gas, in this case CO2. If we double CO2, we expect 3.5 to 4, maybe even more precisely, but say 3.5 to 4 watts per square meter forcing. So if you take 4 watts of forcing, that means a temperature increase of 1.6 to 4.8 roughly in terms of temperature increase. So we can bound the warming, and I think usefully, because if you even say 1.6 on the low end, it's still an appreciable warming, and it's something we should be concerned about. And the high end begins to become rather disconcerting. We know that warming will be amplified over land and in the Arctic. So I think we can say that with great confidence. We feel pretty confident that hot temperature extremes will increase and cold ones will decrease. We can say something about the hydrological cycle. And we can say something about the oceans, about sea level, ice, acidification. Maybe there's a few other things we could say. I'm not certain, but those are the things I would be willing to defend as things that we see as the consequences of climate change. The problem is, most of the things that we can say don't really have much to do with what we're being asked mostly to do. So all of those things tell us we should reduce CO2 emissions. We should mitigate against climate change, because climate change will have these consequences which we don't find particularly attractive. But when you look at this Article 2 and you look at before we had this low greenhouse gas emissions, so those things that we know tell us that we should do this, done. But we're not asked about this anymore. We've done that. The things we need to do is we're being asked, how do we adapt to the adverse impacts of climate change? And how do we foster climate resilience, so adaptation resilience? And the difference between these two things and this one is something that you can make a global statement about. So you say that CO2 causes warming globally, and the way to do it is you reduce emissions of CO2 globally. That's a problem we were good at. These involve problems that we're not good at. So whereas mitigation is global, adaptation and resilience are local. And we have frightfully little idea of what that means. So when you say climate change, the world's warming, how does that tell you to adapt in Stockholm vis-a-vis Helsinki? Does anyone know, as the planet warms, is Stockholm going to be wetter? Will it rain more? And how confident are you of that? Would you be willing to increase your power bill by 30% to prepare for your bet on whether it will be wetter? So when we think of regional rainfall, we don't really have good ideas about that. So on where we're called on by society to do things, we're falling short. So what should we do? So you say, okay, we need to understand something about the planet's warming. It's 1 degree warmer, it's going to be 2 degrees warmer, but what does a 2 degree warmer world look like? What's different about it, other than it's warmer? It seems like something we'd like to know. How should we go about it? And so you could say, well, these are new challenges for our field. It's exciting. As scientists, we have things to do. We're very relevant to the world who's trying to understand what climate change means. And we say, how do we go forward? And one way to address these new challenges would be to say, well, how were we so successful until this point? How did we learn the things we know? And that might teach us how we will learn the things we wish to know. So then let's go through that exercise and say, how did we have this great success that we've really convinced the world that rising greenhouse gases are a threat to the world as we know it? So how did we do that, and does that inform us in terms of how we address these new challenges? So if you go into the literature and you look, one of the things you'll see is that models are becoming increasingly realistic. And here this is illustrated by cartoons. If you just do a very superficial thing and go through the reports, once upon a time we had models which looked like schematic arrows. This was a picture that's in AR1, and it was also actually drawn by Larry Gates, where he conceptualized the Earth system. And at that time they were saying we have to put models together to understand things. And if you flip through the different reports and as we portray our world, you get the impression, and I think most people would say this, that our representation of the world is becoming increasingly realistic. So our models are much more realistic than they used to be. They used to be these sort of schematic cartoons, but now we really have all sorts of things. You have to look in here. We're building the effect of urban areas and how that affects dusts, and we have river estuaries and carbon transport to the ocean. So the way in which we're representing the system is becoming much more realistic. And look, if you go through time from the 70s to the 80s to the 90s, the late 90s, the early 2000s, 2010, these are the different, again, the assessment reports, AR3, 4, and 5, if I got that right. What you have is if you just follow this as time, and this is process complexity, and it paints this picture of progress, where in the beginning, it was kind of like the Bible, kind of adding the animals and the people, and so we do this too here. So we have the atmosphere, and then we have the land surface, and then let there be ocean and land, and then let there be oh, look at this, this is Henning here, sulfur. Let there be sulfur, so then there was sulfur, and then let there be non-sulfur, and there was non-sulfur, and let there be carbon. And so we go on. This was kind of too schematic for the AR4, so they put it in pictures that people could understand. First, the world looked like this. There was rain but no clouds. It's interesting in models this happens too, is that the clouds come after the rain. The rain makes, so then we had clouds, and then we had a swamp ocean and an ocean that was deep, and look, here's Henning again, sulfur cycle, that work started here. Aerosols, and then chemistry doing all sorts of things here. And here it even goes, another point is made, it's not only that we're adding things, is that we're getting better at the things that we do. So the atmosphere used to be very simple, and then we added land, and then ocean, and then aerosols and carbon and so on. Henning dropped out of this picture. But the atmosphere also got better, so these boxes get deeper. So the things that we have are getting more realistic. If you fast forward to the AR5, which is slowly becoming old, they have this diagram here. And what it tries to show is different ways of looking at models in terms of their mean state, their trends, their variability, and their extremes. And then it has these two axes, this model performance axis and the confidence in the assessment axis. And so here we have low confidence and poor performance. And then it tries to put different things that fit in these boxes and color them according, so there's lots of information here, according to whether things have gotten worse, red. So according to this diagram, there's nothing that's gotten worse. That's good, so the models aren't getting worse. There's quite a few things that haven't changed in the sort of 5 or 7 year. But there's actually quite a few things that are getting better, which are green. So all these green things are getting better. So according to this diagram, lots of things are getting better. And as they get better, we move up into this model performance and confidence in assessment. It's a funny thing because improvements since CMIP 3, it's kind of hard because if it was improved, then I don't understand, because then blocking is here, but then if it's improved, it should be here because the model performance is better. So it's a funny diagram, but maybe the performance isn't that much better, so it still stays in the same spot. I'm not sure how they thought of that. So the models are getting better at everything, and even when they're not getting better, we're getting clever. So we have great things like what are they called? Emergent constraints. So even when the models are wrong, we're clever enough to realize that they all happen to be wrong in a certain way that allows us to use measurements to figure out what they should be doing. So in this idea is you take an observable and you find a reason why an observable is related to something that's not observable but you would like to know. And if you find a relationship between an observable and something that's not observable but you would like to know, then you can constrain the relationship by observing the observable and then inferring what you would like to know. So we have this idea that, okay, even if the models aren't getting better, we know how to extract information from them. So it's a wonderful narrative. It's that models simulate the climate system based on physical laws. I wrote partly the AMS statement on climate change, and we had a rather vigorous discussion about how to phrase that. So models, and people are fairly insistent on emphasizing the fact that models are rooted in fundamental physics. You hear that again and again, right? Models are rooted in physics. They're based on fundamental laws. So we have that. Increasingly so, as we account for more and more relevant processes. And the existing processes are more realistic. Often as a result of increased understanding of the Earth system is derived from careful and comprehensive observations. So if you read the IPCC report and you go to one of the meetings with policymakers and if you talk to the government, I don't think this would be, maybe I'm not presenting it quite as convincingly as some of my colleagues might, but I think people would, this is what we often say. As a result, the ability of the models to simulate the climate system is steadily but unambiguously improving. So our models are getting better. We can simulate more things. And even in cases where biases persist, we're becoming clever in finding ways to correct or factor out these biases. So the result of the narrative, if we say, oh, we're called on for this new task, we have to provide understanding of regional changes, is that we're on a good path. We're good. I mean, climate scientists is there where society needs it. We're making progress, and if you just give us a little bit more funding, we'll make more progress. So I would say that's one narrative you could have. Another narrative, which we could have, and then you can decide which one you like better or where in between the two narratives you might fall, is that nothing that we claim to know really has anything to do with the fidelity of our most comprehensive models. So if you go back to those statements that I made at the beginning, then I would ask anyone, and you can say at the end of the talk, is there anything that we know and believe about climate change that we know and believe because we made a change in a model to make it better, and now we believe it where we didn't believe it before. I can't think of one. Model biases remain large, and for almost every signal I've looked at, as large as the signals that you're trying to predict, even global temperature. If you look at globally average temperature, a model that's run out of the box has a temperature error that's larger than the warming that we've experienced in the 20th century. Most model development does not critically use data and cannot meaningfully be distinguished from curve fitting. That would be another narrative, is that we actually don't use data. I work in a modeling center, I interact a lot with modeling centers, and I think you could make the narrative that actually they don't need another piece of data at all. And even if you gave it to them, it wouldn't matter, because the reanalysis is enough, and there's enough problems matching the reanalysis. And so data is sort of like kind of an accessory that you have that makes you look good when you go out. But it's not something that you really need. Strategies for post-processing model output are based on the premise that all models are wrong, but just in the right way. So here you could look at this figure again differently. For this to work, for the emerging constraint to work, the models have to be wrong, because otherwise they don't spread. So you need spread. But they have to be wrong in just the right way. If this curve was up here or down here, or if this relationship wasn't because they somehow got a physical relationship that's right, just wrong in a certain way, then this would have no meaning. So our post-processing rests on the premise that the models are wrong, but they just happen to be wrong in the right way. Could be. In some cases it's probably true. But do you really want to go to society who's thinking of spending trillions of whatever unit of currency to say that, you really need to build more changes in the water system in Stockholm because, our models are wrong in just the right way that makes us realize it's going to rain more? Is that something we'd be happy with telling society? And we're better at making graphs, and we spend a lot of time on uncertainty quantification. But part of the narrative could be this uncertainty quantification, which so dominates our field, is really just an illusion of precision. It makes us seem precise. The models just have to be better quantified. So if I say this among my colleagues, some people will say, oh, you're just model bashing. So you could ask, how much is there evidence for this stuff? I come from a modeling center, and one of my most cited papers is a modeling paper. But it doesn't stop me from being a model basher. So go to this thing of, what knowledge comes from the fidelity of our most comprehensive models. And I would say most of what we know, those statements I said at the beginning, actually we learned in black and white. That means they came out in journals before journals had color and before Eula was born. Because I guess, I don't know, she's not older than, what would that be, 36 or something like that. So this is a fantastic paper from Nordhaus, 1977, an IASI report. And it's the earliest I know of this attempt to really, I have to look if Wally Brooker has something in 75, but really to look at the transient climate sensitivity. And so he had this little thing, this is the warming, the calendar warming, and this is, the aerosol or volcano mix of stuff here, cooling, ice age. No, he said no ice age, we're going to warm. And if you actually look at his prediction, this is kind of my best fit to that first curve that I drew. It's pretty good, So, and this was based on physical reasoning and simple models. It wasn't because we got the latest change in the cloud scheme or the ocean mixing in the latest version of EC Earth. Polar amplification, warmer continents. This is Manabi and Stufer, 1980. Very simple climate model, really one of the first ones to put realistic geography with a swamp ocean, and made the argument and physically reasoned why it makes sense. It missed some pieces. The polar amplification was mostly a snow albedo feedback, and since then we could say we think there's evidence that this probably has as much to do with stability feedbacks as well as ice albedo feedbacks. But this idea is rooted in very simple arguments that were present in really relatively crude GCMs. And here, a lot of people don't know this, but this idea of wet get wetter, dry get drier, that goes actually back to Mitchell in the 80s. And so he did in 83. And what he showed here is this is the precipitation. And he argued that the precipitation changes are mediated by the existing precipitation, or precipitation minus evaporation, exactly what Held and Soden did, which Held and Soden are more known for this. And he did this because he had two versions of the Met Office model, something called 5M and 11M or something like that, and they had very different hydrological cycles. But the change in precip, you see here it increases, here it decreases, here it increases, here it increases, here it decreases, and then here it increases. So he argued based on this that really what should happen is the hydrological cycle should be amplified for very physical reasons that you didn't need a very complex model for. So you could say these are the things that I put on my early slide, things that we know. And you know, I would maintain that we know them because they're based on simple ideas that some of the earliest and crudest models helped us understand. And sometimes I say that, is that so what have all the better climate models done for us? It's not that they're useless. You know, I'm not at all saying that this whole effort that we've done has been useless. But when you look at a result like this, you can think of lots of reasons why you wouldn't believe it. So you spend 30 years working through those reasons with more complicated models and see if you're surprised. And what you find is you're not. So the contribution, I think, of the big model development that we've been doing for the past 30 years hasn't been that we make better models that are so much more reliable. It's that they've made us feel comfortable with the simple arguments that we had before, which we, on the surface of, we could have thought of a lot of reasons why this might not be true. But after working through those reasons, we say, well, actually, no, this seems to be the dominant physics. We more or less got it right. Same thing with this, same thing with this. So the comprehensive models until now have mostly been successful for what they don't show rather than what they do show. That's part of my claim. Model biases. So I claim that, you know, when I went back to this other narrative, maybe I'll just go back here again. Model biases remain larger. So let's look at model biases. If we look on the right column here, this is precipitation changes towards the end of this century, 2081 to 2100. And what we show is millimeters a day precipitation and just maps of June, July, and August precipitation changes. And there are three models. And if you look closely, you can see some things in common, like a sort of Mediterranean, Southern European drying, and maybe a warm pool moistening. But you can also see, you know, rather large differences if you look from place to place in terms of the models. Not just quantitative, but also in terms of qualitative thing. Like if you look here in the Atlantic ITCZ, it produces moistening and drying, and here it's drying versus moistening. And if you say, okay, we could try to post-process these. We could try to filter and see where the models are common and where they're not common, and we could say we have confidence if they have things in common and not confidence if they don't have things in common. But in a way, these models are all more or less trying to solve the same problem. They're not really doing, they're different implementations of the same ansatz, the same way of formulating the problem. And just because they get things in common doesn't mean that that's what's going to happen. Because if it did, then you would expect them to have much less bias. And here's the bias, actually. And the remarkable thing about this is if you look at nothing and you ask which picture has more color, this one has more color. So the biases are larger than the signal in precipitation. People would say, oh, precipitation's hard. That's not fair. So look at temperature. Temperature is easy. But normally when we look at temperature, we look at globally average temperature. And so you have the mean signal. We know that. Okay, we all agree. We did that, we're good. But we want to do more. And this is the deviation from the global average in the models. And this is the bias in the models.
So from where do you get the bias? Is it reanalysis?
Yeah, so we use the reanalysis.
Because they also have a lot of uncertainty.
Yeah, but for temperature, I think they're probably not bad. Probably not this bad. And it doesn't matter because the biases aren't consistent, right? So even if the problem was the reanalysis, then and the models were actually doing better somehow, then you would say like this might be, you could argue maybe this is a reanalysis, but this one gets a different color. So even modulo reanalysis error, I think you would still find large color here. So I agree, the reanalysis is also limited by the biases in our model. And again, the point is that the biases are as large as the signal. Fine, I mean, if we're just playing with a hobby, that'd be okay. You know, we'd say, well, the bias is as large as the signal. But if you know, the thing that kind of gets me, I kind of like your Greta Thunberg, or however you say her name is. What I like her is because she's like saying, wake up, people. You know, is this important or is this not important? And if climate change is important, is this good enough? And many of my colleagues spend all their time going around to scratch their head and say, oh, why aren't the politicians doing anything? And I'm like, why aren't we doing anything? I mean, how are we happy with that? And then we come back to this idea, are climate models good enough? You know, are they really? We like to say climate models are constrained by the laws of physics. And here, this is something we put together for the last IPCC report, and it shows a section off the west coast of North America, stratocumulus region. There's Frida's postdoctoral location down here. What we do is we cut through a mid-latitude eddy. And what you have in mid-latitude eddies, it's really the fluid dynamics of a rotating fluid, where the rotation imparts a rigidity on the flow that allows you to simulate things in a sort of quasi-two-dimensional sense. And what you get is you get, you know, large-scale ascents and large-scale descents. And the cloud systems in these things are what climate models were designed to do. So they were built around this idea. And in fact, the predecessors of today's climate models were really built on looking at how to transport heat from the equator to pole by these eddies. So if you go back 50 years, that was a big problem. If you think of the climate system, what does it do? It gets all of its energy, all exaggeration, but all of its energy at the surface near the equator. And the job of the climate is really to do two things. One is to put that in the atmosphere, A, and take that to the pole, B, and then it radiates it away. So the circulation moves the heat around so that it can be radiated away. And this part of the heat motion was a big climate problem in the days of Budiko's models. They had to parameterize the eddies. Smagorinsky said, we don't need to do that. We can simulate them. He was embarrassed, but he did it anyway. And we never looked back. But we forget that in the tropics, the other half of the planet, all of the heat transport is mostly in the vertical, and it's mostly non-hydrostatic and associated with cloud-mediated radiative responses. There's nothing fundamental in how we do this. Here we use Navier-Stokes equations, the laws of fluid mechanics. Here we use sort of seat-of-the-pants reasoning that says an updraft goes like this and a downdraft goes like this. The way we treat this isn't fundamental. This is like a Budiko model, you know, the way we treat the vertical transport. So these models aren't, you know, for very important things, they're not rooted in the laws of physics. For very important things, they're rooted in seat-of-the-pants reasoning, which we know matters. So that comes back to my preaching here. Is climate change important? I don't know. But if we think so, how can we be happy with the state of our science? We spend, as scientists, so much time lamenting the state of our politics. And I decided I'm going to lament the state of our science. And I think one of the problems is we're scared to talk about the things we don't know. Because many of us are afraid that if we talk about the things that we don't know, disingenuous people will use those to say that, to cast doubt on the things that we do know. And I say screw them. You know, we know what we know, we're confident, and I'm happy to talk about the things we don't know. And if you try to call me on the other things, I'll say, you know, go to hell. The climate is warming, our planet's changing, and I don't think we really have a good idea of what that means. And sometimes where I like to speculate is the tropics. So half of our planet is the tropics. All of the models use a similar ansatz. They all have different tropics. All the models have different tropics. If suddenly I said, today we live in a world with the Hadgem tropics, and then I said, in 20 years we're going to switch to a world with the